Okay, so in the last video, I gave you a very complicated definition. And what we're going to do today, that's this thing right here, this definition. And what I'm going to do today is try to show you why, oops, let me do it this way. I'm going to attack that problem right there. And remember that A plus is the area above the x-axis, A minus is the area below the x-axis, and what I'm saying here is what this sum is going to represent is the area above minus the area below. That's today's goal. So what I'm going to do is I'm going to ask you a question, and I'll answer it, of course, and the problem is find the area bounded by the graph where f of x is greater than 0. In general, well, I'll expand that later. X equal a, which is this line right here, x equal b, which is this line, and the y-axis, which is, of course, down there. So the way I'm going to do it is I'm going to approximate it with 3 rectangles. And then we'll add the area. Okay, so, and by the way, I'll have you do an exercise where you do this. So I'm going to pick, to prove a point, I'm going to pick 3 rectangles. I'm going to draw them randomly. There's one. Here's the second. And then here's the third. And then right there, right there, right there is where the rectangles hit the graph. I'm going to call those points C1, C2, and C3. Okay, and notice that this point here is going to be C1, f of C1. There's a lot of notation. This point here is going to be C2, f of C2. This point here is C3, f of C3. And notice that the height of each rectangle is this number right here. That height is f of C1 from here to here. This height is f of C2. And this height over here is f of C3. Okay. So what I'm going to say is that the sum of the area of each rectangle equals, well, approximates the area under the graph, meaning this area under here. Okay, now, everybody buy that? That if I add up these areas, what I'm going to get is I'm going to get an approximation of the area under the graph. And I'm probably going to get a little bit of an undercount because, as you see, I'm missing a lot of area. But it's an approximation, and that's all I'm after right now. So what I'm going to do now is I'm going to figure out the area of each rectangle. So the area of rectangle 1 is going to be the height times the width. So this is going to be my first width right there. This is going to be the width of the second, and that's going to be the width of the third. So I'm going to say width 1, width 2, width 3. Now, in other words, this width we're going to write as delta x1 because it's going to be the change between these two x's. And these values here, that's going to be delta x2, and this is going to be delta x3, this area right here. So I have height times width, so that's going to be f of C1 times delta x1. So that's this rectangle right here. Now the area of R2 is equal to the height times the width, and that's going to be f of C2 times delta x1. And then R3 area, I'm running out of space, that area is going to be equal to the height. So that's going to be f of C3, this height right here, times delta x3. I'm sorry, this should be delta x2. So in other words, the area of this rectangle is height times width. Height times width. The area of this rectangle is height times width, height, width. And for rectangle 3, the height times the width, height times the width. So I'm going to say that the area under the graph is more or less equal to, approximated by, the sum of these three areas. Okay, everybody agree with that? I think that's pretty intuitive. Now, again, I'm going to change this a little bit, but I'm going to work with this, then I'm going to come back to it, and I'll refer to the picture. But keep that picture in mind. So, I'm going to look at this right here. This is equal to what's called a summation. There's 1, 2, 3 things, so I'm going to have 3 rectangles. Now, each term here has an f in it and a delta x. So the way you represent this mathematically is call that ck. So ck would be c1, then c2, then c3, and call this delta xk. And this is a summation. And it's also called a Riemann sum. And let me explain the notation. If I give you something like this, pretend you haven't seen this before, then the way I think of the summation is first you let k is equal to 1. And so wherever there's a k here, I plug in 1. So I get f of c1 times delta x1. Then you let k is equal to 2. And you do the same thing. You write what's here, and you put 2's in. Whoops, I didn't leave enough space. And then you let k is equal to 3, and that's where you stop because that's equal to here. Because n is equal to 3, the stopping point is equal to 3, and I do the same thing. That's 3, and that's 3. So what this is shorthand for this. Okay. So what do we say? The area under the graph is more or less equal to this summation. And this is what that summation, the area under the graph is equal to these 3 terms. We abbreviate it by this summation. So my point is that the area is more or less equal to this sum. So again, let's look back to see what I'm representing here. I think it's worth going through this. Sorry, wrong picture. Excuse me. Here's the right picture. Okay. Okay. I'm trying to find this area between B and A. I divided things into 3 rectangles, computed their heights and their widths, and I added together, and this is what I get for each of the areas. This is area rectangle 1. This is the area rectangle 2. And this is the area of rectangle 3. Okay. So this area in the rectangles is that, and this is about equal to, this can be represented by the summation. So in other words, the area under the graph is approximated by this summation. Okay, that's the main point that I want to make. So area under graph. Okay, makes sense? Okay, I hope it does.